Welcome back, everybody. Hope you're having a good one. Today, we're going to continue our discussion about the turbofan engine. We're going to go through some of the engine matching conditions, some special notes about areas at the face of the turbine, some non-ideal factors, and then we'll end the lecture with a kind of a fairly involved example involving a turbojet. And then next time we will, and then we might conclude with a note about afterburners. We'll see how long all of that takes. But then in the end, we'll transition to, in the next lecture, talking about turbofan engines, and that'll be the last topic of the course. Okay, so let's go ahead and proceed from where we left off. We had left off talking about the optimal compressor ratio, and how at a certain point, once your speed reaches a certain point, then you would want to the ramjet becomes the way to go, because you don't need a compressor anymore. But the next thing that we wanted to discuss are the so-called engine matching conditions. So really, like I said before, when we talk about matching conditions, really all we're doing is we're doing, energy balances and specifically mass balances between different stations in the engine. So like for one case, we have this turbine nozzle matching. Which is where you say the mass flow rate at station 4 is equal to the mass flow rate at station 8. Okay, station 8 is the nozzle throat, remember? So that, at this point, hopefully this sort of mass balance equation is becoming familiar. You end up with this balance right here: PT8 A8 over the square root of TT8 F of M8, and then usually the nozzle is choked at the throat. So M8 is equal to 1, and therefore F of M8 also goes to 1. Okay, but there's this thing that happens in a turbine. So the turbine is composed of many stages of what are called stators and rotors. Okay, so the stators are stationary airfoils that are kind of shaped like this. This is kind of looking at a cross section where the flow would be coming in from the left. Okay, so they're these like high angle of attack airfoils basically, but in reality it's a bunch of fan blades. And then you have a rotor, which are these sort of anti-aligned airfoils on the other, directly downstream, and those are on a rotor that rotates, of course. Okay, and so you actually get a very large pressure drop per stage. So very large pressure drop per stage of the turbine, and because the stator airfoils or blades have a very aggressive angle of attack, and so because of that, the boundary layer stays attached, and the pressure drop causes the flow to become choked on the first stator. Okay, so you have this really hot flow coming in from the burner, and then it becomes choked kind of right at this area here, okay, where I'm putting my dashed line. And if you sum up all this dashed line area, you end up with this area that we call A4 star. Okay, the actual A4 is at the face of the turbine. Okay, that's A4. But A4 star is this reduced area at which the flow is getting choked on the stator, the first stage stator. Okay, so what we do is we actually A4 becomes like one of the design parameter areas that you know, or you at least know the ratio of A4 star to A8 as like a design parameter. And the reason why is because the flow is choked there. That means that flow is choked at the location of A4 star. That means that M4 at that point, or M4 star I should say, is equal to 1. Okay, and so if we instead, and then we say that the stagnation pressure, because there's, remember I was talking about a large pressure drop here. We're talking about static pressure when I talk about pressure drop, but the stagnation pressure is not changing because the flow is isentropic between station 4 and station 4 star. So the stagnation pressure at station 4 star is the same. So since isentropic, PT4 is the same as PT4 star. And there's also no heat. It's also adiabatic, which is a subset of isentropic, I suppose. So TT4 is equal to TT4 star as well. Okay, so then we can basically replace A4 in the mass balance above with A4 star, and then the F goes away. And we can do the mass balance between station 4 star and the throat of the nozzle, and you end up with this PT4 times A4 star over the square root of TT4 is equal to PT8 A8 over the square root of TT8. Both of the area Mach relation functions go away because the flow is choked at both of these stations. Okay, and this is nice because we can now rearrange this and write out the area ratio A4 star over A8 in terms of just the ratio of these stagnation pressures and temperatures. But the real trick comes in when you see or when you assume that the turbine is operating ideally, or if you assume that the turbine and the nozzle are ideal. Okay, so let's say, assume nozzle and turbine are ideal. Well, what does that mean? Well, first off, if the nozzle is ideal, that means that PT8 is equal to PT5. Okay, and TT8 is equal to TT5. And then the turbine being ideal means that pi t is equal to tau t raised to the gamma over gamma minus 1. Okay, and that has the following effect. We can take this A4 star over A8, and we can write that in terms of the pressure and temperature ratios across the turbine, because PT8 and TT8 are just equal to PT5 and TT5 respectively. So you end up with pi, the pi of the turbine divided by the square root of tau t, right? And we have also this relationship here, and so that allows us to simplify even further, where we have tau t raised to the gamma over gamma minus 1 times tau t raised to the for simplicity, making this a little bit more simple to write. I'm just going to write this as gamma minus 1 over 2 times gamma minus 1, because that's the same thing as the square root of tau t. And so we can add these things together, and you get the following, where you can actually just write the turbine temperature ratio, tau t, in terms of only these area ratios. It's determined, this sort of, the tau t and pi t, since they're the turbine's ADO, are determined entirely by the area ratio from the inlet of the turbine to the throat of the nozzle. Okay, so we can write tau t as A4 star over A8 raised to the power 2 times gamma minus 1 divided by gamma plus 1. Okay. So that's an interesting fact to keep in mind when you have an ideal turbojet. In fact, we'll probably, I think we use that in the example that we'll do later in this lecture. You can also do some matching between the compressor and the free stream. So compressor, free stream. So what that boils down to is just a mass balance, PT naught, A naught over the square root of TT naught. F of M naught is equal to PT2, A2 over square root of TT2, F of M2, and then we assume we're assumed that we're still an ideal turbojet, so there should be no shock in the inlet, and in that case, TT naught and TT2 cancel out. They're both the same thing, and you can write F of M2 as 1 over pi d, which may itself be equivalent. Actually, I should say this TT naught and TT2 are actually the same regardless of whether or not there's a shock in the nozzle. PT naught and PT2 might be the same if there's a shock in the nozzle. So pi d, which is how you would just express PT2 over PT naught. That might not be 1. That would be 1 if there's no shock in the inlet. So this is actually generalizes. But the way you can write F of M2 is 1 over pi d times this area ratio A naught over A2 times F of M naught. Okay, so that's one matching condition. There's also the matching between the compressor and the turbine. And here we use that 4-star state again. We're going to keep this time take into account the fact that we have fuel, mass flow rate addition across the burner. That's what this 1 plus F is doing here. And we have PT2, A2 over the square root of TT2, F of M2. So if you're ever going to do a mass balance and you want to take into account the fact that you have a non-zero lowercase f, you just stick a 1 plus f factor on the side of on the station, or the side of the equation that corresponds to the station that's before the burner. Okay, as long as you throw that in there, then you won't violate mass conservation. And you can prove that to yourself if you like. And then see a PT4, A4 star over TT4, square root of TT4 rather. Okay, and then we can then write F of M2 in a different way. F of M2 in this case would be 1 over 1 plus F times pi C, pi B over the square root of tau lambda over tau R, okay, times A4 star over A2. And then if we, assume that the burner is ideal, and ignore the non-zero f, the expression becomes simpler, where you just have pi c over the square root of tau lambda over tau r times that area ratio, A4 star over A2. Okay? So that's nice. And then there's also the shaft energy balance. So the shaft energy balance, I'll just write it in its already normalized form. It's easy enough to obtain on your own. Times 1 minus tau T. Okay, so that's the energy balance across the shaft, assuming no losses. And these sorts of matching conditions are useful. You can use them directly yourself, but I would actually just recommend just starting with the mass balances and coming up with expressions like this in your analysis, and not kind of looking for these specific formulae in your notes and using them plug and play. I think you'll experience more success if you just do the mass balances from the beginning. Okay, so the next thing that we want to discuss is this idea of capture area. This is a little bit of a tangent, I'll say, but it kind of gives, it's a little bit of a discussion that can give you an idea of the engine operation and engine design a little bit. So the overall purpose of the inlet is to provide the engine with airflow at the correct Mach number with as little stagnation pressure loss as possible. Okay, so the way we find that Mach number is by starting at the nozzle and moving forward. Okay, so generally, if you want to make sure everything matches, you start at the nozzle with like a really small exit area, and so therefore you know that the flow is choked, and then you kind of start your analysis from there. So if you can draw this case like this, right, where you have just this kind of empty engine for argument's sake, and we have this really small A8, okay, and then we have our inlets right here, and we know that the flow is choked at station 8, and so small A8, which means it's choked there. We know that we have this idea of a capture area. So we're going to say that we have this area here, which is like A0. Okay. So if we do a mass balance between station 0 and station 2, say, we know that A0 has to be small. So small A8 implies that we have A0 as small as well. Okay, and it looks kind of like this. It's like a kind of the capture area A naught is this concept that we drawn out here. Okay, and if we increase A8 a little bit, so now it's not so small. It might look similar here in the way I've drawn it, but let's say we've increased A8 a little bit. Now we'll say that the capture area is equal to A1. It just increases. So as A8 increases, F of M2 increases. You can see this if you do a mass balance between station 2 and 8, which is the same thing as M2 increasing as well. And so, F of M2 being larger means that A0 is also increasing. Okay, and then eventually the inlet itself is going to become choked. Okay, so with an A even larger than that, station 8, your inlets will become choked, and your capture area becomes larger. So A0 becomes bigger. So eventually, inlet becomes choked. Okay, the way you can kind of you can obtain the choking condition for the inlet by looking at the mass balance between station 2 and station 1.5. So TT2 F of M2 is equal to PT 1.5 times A 1.5 over the square root of T 1.5, F of M 1.5. So this guy goes to 1, right? And so when F, and of course the stagnation pressure and temperature, since there are no shocks, are both equal, remain the same between station 1.5 and 2. So these all cancel. And when F of M2, or when M2 reaches the point such that it is F of M2 is equal to the area ratio between 1.5, station 1.5 and 2, that's your inlet choking condition. Okay? And then if we want to increase A8 even further, okay, so now we'll just have the inlet be much larger. What happens then, since you've choked the nozzle already, or the inlet already, you're going to necessitate a shock in the inlet. So downstream of the throat, you'll end up with a shock. So further A8 increase leads to a shock in the inlet. And the reason for that is because if you look at PT 1.5 times A 1.5 times F of M 1.5, this is still 1, like before. And we have PT2, A2, F of M2. The stagnation temperatures are, they're not affected by the shock, so those still cancel. But F of M2 is bigger than it was before, right? So this is larger now because we've increased the area further on downstream. I don't know why my schematic here is getting shorter and shorter. Here, let me fix that really quick. That's funny. I think it's because I'm like trying to make the engine seem like the exit area is larger and larger, and its aspect ratio is playing with my brain. So we still have the same large capture area here at A naught, but now we're getting a shock. And so since F of M2 is larger, that means that PT2 must be smaller than PT 1.5, right? Just to maintain this mass balance. And that means that you're getting a shock. Some sort of mechanism needs to come in there to supply that drop in stagnation pressure. And then this is where performance starts to rapidly drop off. Right. So in general, you don't want to increase your mass flow rate or your outlet diameter too much to the point where you have shocks in your inlet. Sometimes shocks in the inlet are useful for control, but not in this case. And yeah, we kind of did. This is similar to the reasoning that we did for the ramjets, so it's actually like in reverse. Okay, so that's this discussion about capture area and how you can control that inlet operation by changing your downstream design design choices. Okay, so let's also talk about some non-ideal factors. So this is when your turbine or your combustor or any of your other components have losses and don't operate in a perfectly ideal way. So first thing is actually for the combustor in shaft. The way that we define these is by looking at the enthalpy change and comparing it to the total amount of enthalpy that's being supplied by the fuel. So in other words, we look at 1 plus F times HT4 minus HT3. Okay, that's that enthalpy change across the burner. And we compare that to F times HF. And actually, in general, this is always very, very close to 1. Okay, so the combustor the burner is very efficient in that way. And then there's also this mechanical efficiency, which you can look at by comparing the sort of enthalpy or heat that you're getting out of the compressor to the amount of heat that's being taken out of the flow by the turbine, which is what you see on the bottom here. Okay, and that is also usually very close to 1 in practice. Okay, so we're safe ignoring these losses for the most part. Okay, the main losses that are going to occur are compression and expansion losses. So main losses are compression and expansion losses in the compressor and turbine. So on like a TS diagram, for example, normally we're starting from station 2 here, and then if we assume that it's isentropic, we're going along an isentrope up to 3, and we'll label that 3S for an isentropic state. But in reality, you actually kind of go, here, let me label axes here, TS. But in reality, you actually have some entropy production, and you go over here to a slightly higher temperature, actually, and some higher entropy value, like a real station 3. Okay. And so this is the compressor case from station 2 to 3. And the way we define the efficiency of the compressor is by looking at what the enthalpy would be, sorry, not 3.2, but 3S, would be in the isentropic case. So the change in enthalpy if the compressor was operating isentropically, and we divide that by the change in enthalpy that was actually realized. Okay, so we can rewrite this in terms of the compressor pressure ratio by writing pi c raised to the gamma minus 1 over gamma minus 1 over pi c raised to the gamma minus 1 over gamma times this quantity eta pc minus 1. So what is eta pc? Eta pc is the polytropic efficiency of the compressor. Okay, so eta pc, the way we define that is the polytropic efficiency. Okay, and the way it's defined is as the derivative of the temperature in the isentropic case with respect to the real stagnation temperature. Okay, that's the definition. And so what that results in is that PT3 over PT2 is equal to TT3 over TT2 raised to this gamma times eta PC divided by gamma minus 1. Okay, so normally if eta PC is 1, then you recover that relationship between the stagnation pressure and temperature ratios that we've seen before for an ideal turbine and compressor. But for a non-ideal compressor, you have to include that eta PC factor, and that's what's going on in here. Let me make sure this is very clear. Eta PC. So that's what's going into that formula there. Okay, so that's the compressor case. The turbine is similar but different. Okay, it has a kind of a confusing difference there because of the way that the efficiencies are defined. So normally it would start at station 4, the isentropic path goes to station 5s, and then the non-isentropic path is here and has a little bit less overall compression, or sorry, energy pulled out, so expansion rather. And so what we actually call this is the turbine efficiency is the expansion efficiency. So one is C and one is sub E. I'll try to make that clear, but there will be times when I'll accidentally write a small e that looks like a C, so I apologize in advance. But the way that we define this is kind of like the inverse of what we did before, where we take HT5 minus HT4 and we divide that by HT5 in the isentropic case minus HT4. Okay, and this is just because when you're doing the expansion, you actually get less expansion out when you have inefficiencies. So we're flipping that, whereas with the compressor, you're getting more compression, more heat, right? So higher temperatures when you have inefficiencies and entropy produced. So that's why we have to flip it in this case to get an idea of the efficiency. And so the polytropic efficiency of expansion is the inverse of the polytropic efficiency of compression. Okay, and so what that leads to is the PT5 over PT4 is equal to TT5 over TT4, but you have gamma over the quantity gamma minus 1 times eta PE. Okay, so the eta PE is being multiplied by a different part of the exponent. Okay, it's in the denominator now. And so if we rewrite this expansion efficiency in terms of pi, we end up with this pi t times gamma minus 1 times eta PE over gamma minus 1 divided by the isentropic case, pi t over gamma minus 1 over gamma raised to the power of gamma minus 1 over gamma minus 1. Okay, so these are your that's not good. These are the expressions for non-ideal compression and expansion efficiencies. And typically what you'll be given in the homework is that eta PE or eta PC value that you can use to calculate these efficiencies. Okay. So that's good. Now let's talk about a big long example with the turbojet. Okay, so we're going to do an example that deals with a turbojet that's actually at rest. Turbojet at rest. And I will draw that said turbojet, or a schematic of it at least. And say it just has a simple converging nozzle. Okay, we've got the inlet here. We've got our compressor. I'll just do 3 lines. We've got our turbine. They're connected by a shaft, and we have our burner. Okay, so station 2, 3, 4, 5, then to the exit. Then we have station 1 here, and then it's at rest, so M0 is not equal to 1, it's equal to 0. Okay? Our design parameters are as follows. We have AE over A4 star is equal to 2. A2 over A4 star is equal to 8. T naught is equal to 300 Kelvin. TT4 is equal to 1500 Kelvin. Okay, and then I want you to assume that all the components are ideal. All components are ideal. And then that F is much, much smaller than 1. Okay, and then there's 4 parts to this problem. We want to find the turbine temperature and pressure ratios. In part B, we want to find the compressor, tau C and pi C, compressor temperature and pressure ratios. And then in part C, we want to find F of M2. Okay, and then the last question is what T4 puts the engine right on the verge or the exit rather, not the engine, the exit. Right on the verge of unchoking. Okay? So remember, I said in the last lecture, when we did the example with the ramjet, we want to just start with the stagnation quantities. So start with stag quantities and write down where they are the same and you know, more or less or whatever. Okay, so we don't see any shocks between station 0 and 2. So TT0 is equal to TT2, but then that's going to be less than TT3, which is going to be less than TT4. Okay, so less than TT3 because we're going through a compression stage, and then less than TT4 because there's a burner there, and then that will be greater than TT5 because we're allowing the flow to expand, and then that's going to be the same all the way until TT exit. Okay, and then we have PT naught is equal to PT2, which is less than PT3, equal to PT4, greater than PT5, equal to PTE. So this equivalence here is because everything's ideal, so we're assuming that pi b is equal to 1. Okay, so that's why it's equal across the burner. And then of course the expansion and compression stages should have that the behavior that we wrote down. Okay, so now we can kind of reference back to these guys when we're doing our matching conditions between different stages. Okay, so let's go ahead and get started. Sorry, I was just looking at something for a second. So you're told in the problem that the flow is choked. Okay, so we know that ME is equal to 1, and we know that M4 star is equal to 1. So we just want to use that mass conservation between the two, right? That's and since we're also given an area ratio between AE and A4 star. Now earlier in the lecture we actually just derived this, but I'm going to do it again really quickly. So PT4, just because I think it's good for when we were doing a problem to just start with the, especially for things like exam prep, just start with the mass balances so you don't get confused. M4 star, that's going to go to 1. This is equal to PTE, which we know is actually PT5, right? Times AE over the square root of TTE, which is TT5, okay? Because we just went through the engine and saw where everything was equal. And then this is times F of ME, which we just said is also equal to 1. Okay, so that tells us that 1 over pi t times the square root of tau t is equal to AE over A4 star, which is given to be 2. Okay, but the turbine is ideal. So that means that pi t, or TT is equal to pi t raised to the power of gamma minus 1 over gamma, which makes us able to write that pi t raised to the power of minus gamma plus 1 over 2 times gamma is equal to 2. And we can then write our answer to part A. Pi t is equal to 0.4454, and tau t is equal to 0.7937. Okay, so that's the answer to part A. Really kind of this part that I'm underlining in red, that is just, let's see, just what we derived right here, this underlined statement. Okay. So let's go move on to part B. So we now know the turbine temperature ratio. So in general, if you know the turbine temperature ratio, you can usually find the compressor temperature ratio by looking at the energy balance across the shaft. Okay, so to find tau c, look at energy balance. And if we do that, we get the following. So the general equation is that we have, I like writing everything on one side, so it's always downstream minus upstream. So the enthalpy change, or energy heat change across the turbine, is going to be HT5 minus HT4 times the mass flow rate of air plus the mass flow rate of fuel. However, the mass flow rate of fuel we're going to ignore because F is much less than 1. We're making that assumption. Then we have m dot A times HT3 minus HT2. Okay, if we divide both sides by m dot A, and then also by the heat capacity, since we're assuming a perfect gas as always, we end up with 0 being equal to TT5 minus TT4 plus TT3 minus TT2. Okay, so that's actually an expression of our energy balance. And then we can, in effect, divide both sides by TT4 and then do some algebraic manipulation, and you end up with 0 being equal to tau t minus 1 plus 1 over tau lambda times tau c minus 1. Okay. And then we can rearrange that for tau c being equal to minus tau t times tau lambda plus tau lambda plus 1, which is 2.032. And then pi c is just equal to tau c raised to the gamma over gamma minus 1, which is equal to 11.95. Okay, and again, this energy balance here, we actually derived that in the mashing conditions. It was the last one. It's this guy. Okay. But I just wanted to show you where that comes from a little bit more mechanistically when you're doing a problem. I just recommend doing this because there might be non-ideal factors in a problem that you're doing, and you should just start from the energy balance instead of lifting these expressions from the lecture. Okay, so part C. For C, we're asked to find M2. Okay, and so if you're thinking about this for a minute, we're asking for some information at station 2, and we're given an area ratio between station 2 and 4 star. Okay, so that should sort of scream to you that you should do a mass balance between station 2 and station 4 star, okay? Regardless of what you're asked for, but at some point that's probably going to give you information at station 2, okay? So let's do that mass balance where you have PT4 or A4 star over the square root of TT4 times F of M4 star, which we know is 1, right? That's going to be equal to PT2, A2 over TT2, F of M2. Okay, and we can rearrange that for F of M2, which is equal to PT4 over PT2 times the square root of TT2 over TT4 times A4 star over A2. So that value is given, okay? PT4, because the burner's ideal, is equal to PT3. So that first thing is just the compressor pressure ratio. And then the TT2 is equal to TT naught, right? Because the diffuser, the inlet is ideal. And that's just equal to T naught because we know, because the flow is stagnant, the engine is at rest. So what we can rewrite this as is just pi c divided by the square root of tau lambda times 1 over 8. Okay, and then what we get there is 0.668. Okay, so that's part C done. Now let's do part D. We're on the verge of unchoking. So that means that verge of unchoking means that you've changed the geometry of your nozzle such that we still have ME, the exit, being equal to 1, okay? But we've changed the geometry such that the flow is expanded to a static pressure that is exactly equal to the ambient pressure, okay? So you can write that as PTE over PE, which would be equal to PTE over P naught, which is a given value. I believe it was given in this problem. Oh no, it's not given in this problem, but that won't be important. So the ratio between PTE and P naught is equal to 1.893. Okay, and this value is just the 1 plus gamma minus 1 over 2 times 1 squared. Okay, raised to the gamma over gamma minus 1. Okay, that's how you get that value, that 1.893. Okay, and so this is the general choked flow condition that we discussed earlier when we were talking about converging, diverging nozzles. Same thing going on here. Okay, so then what we can do is we can write out PTE over P naught as a string of over PT naught, which is the same as P naught really, as a string of pressure ratios. So pi D, pi C, pi burner, pi T. So we're just working our way back through the engineer, pi nozzle. Now everything's ideal. So pi nozzle and pi D are both equal to 1, and so is pi burner. Okay, and we just said that this thing is equal to 1.893 when we're on the verge of choking. So therefore, the compressor pressure ratio is equal to 1.893 over pi t. But pi t is the same as before. Okay, since the exit is still choked, our analysis in part A is unchanged. So pi t is the same value as before. So that allows us to calculate pi c in this case, which is 4.25, 0. Okay, and then we can return to that energy balance. So return to energy balance. And we're going to rearrange it. So it's TT4 is equal to TT5 plus TT3 minus TT2. Okay, and then we can just solve for TT4 using all of our ratios. This is just algebra in between these two steps here. 1 minus tau t times t2, which is just t naught. And we end up with 744.5 Kelvin. Okay, so that is what you would have to turn the temperature down to, or reduce your throttle to get your nozzle to be right on the edge of unchoking. Okay, you'd get that temperature down to 744.5 Kelvin. Okay, so that's the reasoning, and hopefully that helps you think through your own turbojet problems when you encounter them. Okay, so with that example done, let's actually have a quick note about afterburners, and then we'll leave discussion of turbofans to the next lecture. Okay, so let's talk about afterburners. Afterburners. So let's say that we're looking at the back half of a turbojet. So we're coming out of the main burner here into the turbine. So this is station 4 here, this is station 5, and an afterburner is a burner that comes after the turbine. So you put a burner here, and then station 6 is the exit of the afterburner, and then you have 8 at the throat, and then the exit here for a converging diverging nozzle. Okay, so the flow exiting the turbine is actually quite slow. Okay, it's not moving very quickly. Remember that the turbine just extracted energy from the flow that it's feeding to the compressor upstream. Okay, but it's still hot, and then the nozzle performs that conversion of that heat into kinetic energy, like we've discussed before. But we can actually heat it up even more with an afterburner. But in general, we say that the flow exiting the turbine is slow enough such that we'll assume that PT6 over PT5, we'll call this pi A, is approximately 1. Okay, so it's like the afterburner is also an ideal burner. May not be true in practice, but that's what we'll assume. Okay, and we also have that AE over A8 is the same as before. And so therefore, your Mach number at the exit is fixed because the throat is still choked. Okay. And so if we then write down this sort of important term in the thrust equation, which is this ratio of VE to V naught, which is TME over M naught times the square root of TE over T naught, right? We can rewrite this in terms of the stagnation temperature at the exit in the following, where we have ME over M naught times 1 over T naught. Okay, none of those things are changing. Those are all fixed. But then we have TT divided by 1 plus gamma minus 1 over 2 ME squared. Okay, and remember that TTE is equal to TT5, which is the temperature at the exit of your turbine, times tau A, okay, whatever tau A you're getting from your afterburner. Okay, so what that means is that your exit velocity is proportional to the square root of tau A. Okay, that's what all of that results on. Okay, so by increasing the stagnation temperature before you go into the nozzle, you get this rapid increase in thrust, because this is an important term in the thrust equation, right? This V over V naught for a perfectly expanded engine, let's say, that term, the thrust is linearly proportional to that term, right? So what the afterburner does is it offers a rapid increase in thrust at the expense of fuel consumption and engine wear. It's really hard on the engine. Okay, I'll just write that down so you have it in your notes. So afterburner offers rapid increase in thrust at the expense of fuel consumption. And engine wear. Okay, now one more note kind of along the engine wear axis, and then we'll call it a day. So if we do the mass conservation between station 4 star and the throat of the nozzle, I don't know why I put M there, I want T there, TT4, is equal to PT8 A8 over TT8. Okay, we can use that to calculate tau T in terms of the following, where you have the square root of tau A times A4 star over A8 times 2 gamma minus 1 over gamma plus 1. Okay, so what does this mean? Well, if we want to, okay, so we may want to maintain the same tau T because we don't want to overstress the turbine, okay? But if we want to do that, we need to actually increase A8. Okay, so tau A is getting larger, or is greater than 1. So A8 needs to get smaller so that we're not stress the turbine. So to not stress turbine, maintain same tau T, you need to increase A8. Okay, and see, this is why you will see variable nozzles expand when they're running the afterburner. Okay, and I'll actually link to a video of a fighter jet that does that. Okay, that activates the afterburner, and you can see the nozzle at the back of the aircraft expand to run the afterburner, to test the afterburner. Okay, so that's just a little note about afterburners. You can see how they operate and some standard considerations. Next time we're going to jump into the turbofan engine, which is the workhorse architecture for commercial aviation, for example. Just sort of you're starting with a turbojet and you increase the complexity by adding another layer with a fan stream and whatnot. We'll discuss it in detail in the next lecture. But yeah, hopefully you enjoyed this one. Again, I'm going to link to I'll link to the afterburner video, but I'm also going to link to a video that's about the SR-71 Blackbird, which has a turbo ramjet engine. It's kind of a combination hybrid between a turbojet and a ramjet. At lower Mach numbers, it runs the turbojet, and then it transitions to the ramjet at supersonic speeds. Very, very great video. It's super detailed. It shows you the shock structures and the inlets and everything. So make sure to go watch that one. I think it's pretty valuable. It's really nice. So I'll put that in the description as well. But yeah, have a good time watching that video. And I will see you next time, and have a great one.